Welcome to part 12, Dents and Gouges. And we're going to kick off this section with the studying we're doing with sort of the introduction, and we're going to deviate into the pipeline code. We're going to quickly go over the fitness for service scope, pretty much the most important things, and then looking at API 510 and 580, which are the inspection codes and how they go hand in hand. Looking at, I'm going to deviate, going to look at dents, in particular dents and pipelines, because there's a lot of good information, and the majority of dents that we find in, that we come across is in pipelines. So we're going to look at, the procedure for doing a high level evaluation for pipelines. And we're going to look at dent fatigue, and then we're going to look at some dent terminology in the API 579. So we'll look. Stay tuned. We'll get right to it. Chapter or part 12, Dents and Gouges, recognizes the following three cases for pressurized components. Okay, and that's key, pressurized components. So if it recognizes dents, gout, which is shown here, and that's a case of a dent, or that's called a plain dent, and the second one is like a gouge, and the third is basically a dent and gouge combination, so which is shown here. Part A begins with a statement saying to evaluate dent, gouge damage on components and combinations thereof. It states that an FFS estimate should be performed in accordance to API 579 as a recognized procedure method. But bear in mind that if we're doing inspection is a key ingredient to doing a fitness for service assessment. For example, 510, if we were looking at pressure vessels, then we would need to use this API 510. And if we were looking at piping, then we'd be looking at the inspection code, the corresponding inspection code for piping, which is API 580. A little bit, and most of this talk will be about dents in pipelines and piping system, because in my experience, that's been the majority of where dents occur. And particularly when I sort of talk about dents and pipelines. And let's look at what they say. So a dent in a pipeline is a local change in the pipe surface or contour. And it can be caused by, pipeline settlement, and that could be at the new construction or the post-construction phase. And an interesting stat is most onshore pipelines have many dents, and most of them are located at the bottom of the pipe, caused by the pipeline originally being laid on rocky ground or on rocks dented by the pipe. The first slide I show you is an experience that I have on a pipe rack. I've seen cases where the wear pad or the pipe shoe the pipe has been misinstalled or it's moved more than necessary, and it's fallen off the pipe support, which is shown to the left here, and then it's caused that local denting in the pipe. I've also seen this where this was inadequately gusseted, the structural frame, and it's collapsed, and it caused denting. So those are common problems. The next one we allude to is about pipelines and the fact that, pipelines do get laid on rocks, and there are dents in pipelines, and it's because of the situations that they're constructed in. Look at some of the standards associated with pipelines that provide some guidance about dents. There's quite a lot of guidance. For example, the Australians have AS 2885.3 operations and maintenance, where they discuss dents. There's also advice on API RP 1160, management system integrity for hazardous liquid pipelines, and we'll get into more details of that this chapter as an example. We're not going to cover all these, by the way, unless someone asks me to specifically. I can do that. ASME B31 for pipeline transportation systems for liquid hydrocarbons and other liquids. There's ASME B31.8 gas transmission distribution pipeline system, the gas line equivalent, gas transmission, and the Z662, the Canadian code, and the U.S. Department of Transport, the liquid rules, and the gas rules also as well. These and reliability people have some rules of thumb about how much it is a dent, a serious issue. And this is one example. It's not every case. Every company is different. I quote these cases from API, and at the end of the next slide, I'll show you where I got them from and where they're used. But API can't be, 579 can't be used, in isolation. There's other phenomena that are going on, or other ways of doing an evaluation without doing the calculation. And some rules of thumb are for immediate response is required if, and I put this in different cases, typically if the dent is located in an area where there's greater than 80% metal loss of the wall thickness, then that's going to have to be done immediately. The second case might be occur if the dent contains a crack. So if you have a combination of two different cases, and then that's another case that we would see as something critical. Another case is located above the 4 to 8 o'clock positions, where the 12 o'clock is at the top, the highest point in the pipe. If there's a dent there, and the dent is greater than 6% of the NPS diameter, then that would be a case of immediate response. Is near-term response, not immediate response. And in the case of the previous slide, where immediate response is required, the API says that you can override these decisions if engineering analysis is conducted. So these are some conditions for near term. So that means do something but you don't have to do it right away. So case one condition, the depth of the dent is greater than 2% of the NPS diameter, or a 1/4 inch dent depth if the NPS is less of the pipe is less than 12 inches. The dent must interacts with a girth or longitudinal weld seam. Secondly, the same condition again about the depth of the dent, but in this case, it has to be located above the 4 and 8 o'clock positions on the top half of the pipe, the closest to the surface. Case 3, it's located where corrosion does not pose a leak. Now here are the sources that I obtain these from, and these are cases are not exhaustive, but they're very typical, and that has to do with these cases, the immediate and intermediate cases. Again, they have to do, um, with because in reality, there's never more than one thing happening at the same time. You could have cracks and denting and gouging, and sort of this helps to sort of make those decisions. So the first one is called API 1160. I'm fairly experienced with that one, managing pipe system integrity in hazard liquid pipelines. Lots of really good advice there. Advice that you get that one. This one here, I've only read it once. It's a more in depth. It's the RP one. It was done by a consultant for the Pipeline Research Council International, and I quote 2018. Recycling it and dents, because we really want to drive home the fact that dents can have an effect on other mechanisms like fatigue. And so, pressure cycling, I have quite a few videos on that. There's some on B31.3 if you want to check that out. But anyway, so here's the phenomena associated with uh, with pressure cycling dents. So basically what happens is, pressure cycles can cause the dent to move up and down with changing in pressure. So the dent that was present may be caused by a dent in a pipe rack or rock, and then the line pressure's up, and it's going to want to form into a perfect circle, because that's the point of least energy. And so it's going to want to straighten out and turn back into like a beach ball shape. And then when the pressure reduces, the the because it's plastically deformed, it's beyond its elastic limit, it will try to spring back to its original position. But of course, it doesn't always go completely back. It's very difficult to predict. So as the line goes through cycling of pressure up and down, this cross section of pipe will begin to fatigue in areas like the corners here, where we would expect to see the most strain. So the dent depth changes in this depth basically induces cyclic stresses of strain within the dent. Now I'm finally going to go back to 12.1 within there, and because I wanted to deviate from a few things, and we'll talk about the scope of part 12 pertains to pressurized components. So structural components, it's not there. So that refers to the dents, which we've spent quite a bit of time in this episode. There's also gouges, and of course dent gouge combinations. And the code allows you to work with these kind of flaws inside or outside the component. And refer to part 5 if there's metal loss characterized with local thinned area, and also refer to part 5 for shell distortions and weld misalignment out of roundness and bulges. So there could be a large number of issues. That's why the pipeline, for example, the pipeline where dents are the most common, they have a lot of rules of thumb to start with, and then the assessment can continue down the road. General, I'm jumping back to the code. I'm going to talk about that this is only applicable to pressurized components. That can, in part 12 only deals with dents, gouges, and dent gouge combinations. Up to now, we've pretty much focused on dents, and as we continue, we're going to talk more about gouges and dent gouge dent combinations, and if there's more interest, more likes, I will continue on to some very, very interesting examples. And reminder that you can do this analysis inside and outside the component. If part 5, if there's metal loss in a locally thinned area, and then you have a dent, then you have to include the part 5 analysis. And for example, if there's shell distortions or anything, and weld misalignment, out of roundness or bulges, then you would have to look at part 8, which I see more in pressure vessels. Dents have a very specific definition in API, and I'm going to just go through it. We sort of touched on it earlier with regards to referencing the pipeline specifications on integrity for dents. And dents is considered an inward or outward deviation of a cross section of a shell member from an ideal geometry that is characterized by a small local radius or notch. And I'll continue here, and you can see a diagram down below. A kinked dent, and I put in here wrinkled because I hear it sometimes considered to be a wrinkled, and is a local radius of curvature at the base of the dent R in any direction of the sharpest part of where RD is equal to or less than the wall thickness RT. 5 times the wall thickness RT, excuse me. And so then if I look here, I have my DR, DPR, and this is my radius T. And so and in this condition here, it would be considered to be called a wrinkle. So let's stop here, and we'll continue on with part 2.